Welcome to the deep dive. We are skipping the discussions about transformer architectures and training algorithms today.
Right.
Instead, we're plunging into the gritty, complex, real world of AI deployment.
The fun stuff.
Exactly. Not how these huge models learn, but how we actually get them to real users fast, stable, and, affordably.
This is truly where theory meets reality. When researchers hand off a massive large language model, the deployment engineers immediately face a completely different set of problems.
It's not a research problem anymore.
Not at all. You have crippling latency, strict memory limits on very expensive hardware, tight cost constraints, and maybe most unpredictably wildly variable user behavior.
Right. Some requests are tiny, some want a 5-page essay.
Exactly. It's all over the place.
And if you look across the landscape of machine learning, we realize LLMs have fundamentally broken the old rules. I mean, if you think about traditional ML inference, say, image classification, it's simple.
So simple.
You feed a fixed input, the model does one forward pass, you get a prediction, and it's done. LLMs are nothing like that.
No, they operate token by token, where the output of the current step becomes the critical input for the next. This sequential, this autoregressive nature, it just completely destroys traditional efficiency.
So that's the core of it.
That's the core.
Right.
LLMs introduce this unique complexity that means the general-purpose serving mechanisms we used for years, they just don't cut it anymore.
They're obsolete.
Pretty much. Our ultimate goal for a production LLM system is speed, stability, and scalability under massive load. And to hit that gold standard, you need specialized engineering.
Okay.
You need an inference engine that can execute those tokens with incredible efficiency and a smart deployment strategy that scales models seamlessly. And that's specialized infrastructure. Well, that's the mission of this deep dive.
Okay, let's unpack those core challenges. You mentioned LLMs break the mold. Why does the autoregressive nature of the model create such a massive headache for the infrastructure?
Well, the need for specialization stems directly from two major technical roadblocks that cost developers huge amounts of time and money. I mean, they just lead to massive inefficiency.
What are they?
First, you have chronic GPU utilization issues. Because requests are so unpredictable and sequential, GPUs often just sit there idle.
So you're paying for hardware that isn't working.
You are leaving massive amounts of compute capital fallow. And second, maybe even worse, you have critical memory management problems, especially around the key value cache, the KV cache.
Oh, the KV cache.
It's an essential component, but it's a huge memory hog, which prevents running larger batch sizes.
And that inefficiency is exactly why specialized systems like VLLM, SGLang, and TensorRT LLM emerged. We're focusing on VLLM today, and we see it tackling these issues head-on.
They do.
The developers clearly articulated the 3 specific problems they set out to solve. First, as you said, those underutilized GPUs. Traditional batching is built on this flawed idea that all sequences in a batch will finish at the same time.
Which they never do.
Never. Second, the really painful problem of wasteful KV cache memory. When the KV cache is stored contiguously, you get severe fragmentation.
Yeah, that fragmentation effectively just cuts the available memory you have for processing requests. It limits your throughput and jacks up your operating costs. It's a killer.
And the third, which is so critical for adoption, that transition from research to production, a difficult developer experience.
Right. So many of these high-performance systems previously required custom code, obscure C++ libraries, custom APIs.
It's a huge barrier to getting these models into real products quickly.
Absolutely. And what's fascinating here is how VLLM tackles these deep, multi-layered technical issues with truly novel strategies. They had to completely rethink memory management and scheduling from the ground up.
So where do we start?
Let's start with solving that idle GPU problem, which leads us directly to the innovation of continuous batching.
Okay, traditional batching, as we said, is frustrating. You submit a fixed number of requests, say 32, and you have to wait for the absolute longest one to finish before you can put the next 32 on the GPU. If one user asks for a single word and another asks for 5 paragraphs, the system just sits there, waiting, leaving those precious tensor cores completely underutilized.
That's the crux of the inefficiency. And continuous batching is the simple but really brilliant solution. Instead of waiting for the entire batch to finish, the system constantly monitors the sequences.
Okay.
As soon as a request hits that end of sequence marker or, reaches its max length, it is immediately removed from the active batch.
So it's dynamic.
It's completely dynamic.
At the benefit.
Well, it immediately fills those newly empty slots with fresh requests pulled straight from the queue. This is happening hundreds of times per second.
So the GPU pipeline just stays full.
It stays continuously utilized. It maximizes throughput without any intervention or special code required from the user's application. You get full utilization, better cost efficiency, and higher performance without even having to think about it.
So if utilization is solved by continuous batching, that just exposes the next bottleneck, that truly brutal memory issue. Let's switch to the KV cache problem.
Yes.
For you, the listener, the key value cache is basically the model's short-term memory during decoding. It stores the results of previous tokens, so the model doesn't have to reread the entire conversation history every single time it generates a new word.
And it grows and grows.
Yeah.
Linearly with sequence length.
Right.
And that cache is absolutely essential. But if you store it contiguously in one big, unbroken block of memory, you run into the fragmentation problem. It's similar to what you'd see in old hard drives or inefficient operating systems.
So because sequences have different lengths, when one finishes, it leaves a gap.
It leaves a gap that is often too small or just an odd shape for the next incoming request, which means you have physically available memory that the system just cannot use efficiently.
So if I'm understanding this right, you're saying you could have, say, 8 gigabytes free, but because it's not in one big block, you can't squeeze in a request that needs 3 gigabytes. That's crippling.
Exactly. It's a disaster for throughput. And this is where Pagedattention comes in, which is arguably VLM's biggest breakthrough. It's a huge engineering lift.
And what does it do?
Pagedattention completely avoids this inefficient contiguous storage. Instead, it stores the KV cache in small, fixed-size, non-contiguous pages. You can think of them as tiny, standardized memory blocks.
Okay, so if the data isn't all lined up in a row, how does the model know where to find the pieces it needs in memory? I mean, it sounds like we're exchanging one problem for another fragmentation for a huge management overhead.
That's a great question, and it's really the core of the solution. It uses a lightweight structure, a block table or a lookup table, that tells the model precisely where each memory page lives.
So like an index.
Exactly like an index. And you're right, this does introduce a tiny bit of overhead for the lookup. But the data shows that the overhead of managing that page table is just massively outweighed by eliminating the fragmentation. You gain so much more usable memory that the efficiency just skyrockets.
So the economic benefit is huge. You eliminate fragmentation, you use your memory perfectly, you support larger batch sizes, and you can serve much longer context, all on the same GPU hardware you already owned.
It's a fundamental change in your cost structure.
So it is.
Now let's wrap up this performance trio with scheduling. This part is tricky because LLM processing involves two fundamentally conflicting goals.
Okay.
You have the pre-fill phase, which is processing the input prompt. That's high throughput, bulk work.
And then you have the decode phase, generating the output tokens one by one.
Correct. And decode is highly latency sensitive. A user sees that first output token and judges the system's snappiness right then and there.
So if you just prioritize throughput, you might batch up too much pre-fill work, and that initial decode time suffers.
It suffers badly. But if you only prioritize speed, you can't get the cost savings of batching. You're stuck.
So you need to maximize the efficiency of the bulk input processing while ensuring the time to first token is lightning fast.
Precisely. VLLM's smart scheduling handles this balance automatically. The scheduler efficiently groups the prefill work together to maximize raw compute throughput. But then, and this is the clever part, it expertly interleaves those critical decode steps between the prefill passes.
So it's switching back and forth.
It's this clever orchestration that gives you the best of both worlds. High overall system throughput because of the efficient grouping, but without hurting that vital user-facing latency because the decode steps are prioritized and interleaved.
Here's where it gets really interesting for complex, real-world applications, not just one-off questions.
Right.
It's not just about raw speed and memory. It's about smart resource management and flexibility when your users start interacting with the models repeatedly, especially in multi-step conversations. Let's talk about prefix-aware routing.
This is a powerful cost-saving measure that leverages user patterns.
Huh?
Many applications rely on shared elements, like standardized system prompts, long instructions, or even the first few turns of a conversation.
These are the shared prefixes.
Exactly. Traditionally, if 10 users start a conversation with the exact same 500 token system prompt, that prompt gets recomputed 10 times.
Wasting compute and building the exact same KV cache over and over again.
A huge waste. Prefix-aware routing minimizes this. The system identifies these common prefixes and ensures that sequences sharing them run on the same worker or replica.
So it caches the result of that initial computation.
It avoids recomputing the KV cache for that shared prefix entirely. And this drastically reduces both the compute cycles and the memory cost across the entire serving system. It's infrastructure intelligently leveraging the semantic overlap of user behavior.
And speaking of flexibility, this is crucial for the modern fine-tuning paradigm using LoRa, or low-rank adaptation.
Oh yeah, LoRa is incredibly popular.
Because it lets developers fine-tune a model for specific tasks without modifying the massive base model weights. How does VLLM handle serving dozens of different LoRa variants efficiently?
The beauty's in the architecture. LoRa adapters are extremely lightweight compared to the enormous base model, say Llama 3.8b. The engine loads that huge base model once into GPU memory.
Yes, once.
And then it applies the various adapters per request without duplicating that massive base model memory footprint.
So the real-world impact there is I don't need 3 full copies of Llama 3.8b, consuming 3 times the memory, just to handle 3 different personalized versions for different customers.
Exactly. Or for A/B testing, 2 fine-tuned variants. It allows developers to easily support personalization, fast A/B testing, and multi-feature applications with just minimal memory overhead.
That's incredible flexibility.
And they also designed the engine so it can host multiple entirely different base models inside one server, which offers incredible density for mixed workloads.
Okay, now we need to address that third initial challenge, the difficult developer experience. The engine can be lightning fast, but if it requires custom libraries and esoteric C++ to deploy, it just creates a moat that prevents adoption.
Totally.
This is why the OpenAI compatible API is such a pragmatic win.
A massive simplification. We found that VLLM exposes the exact same API structure as OpenAI's popular chat completions API.
Which everyone already knows how to use.
Right. So for you, the listener, this means if you already have an application built using the standard OpenAI client libraries, migrating to a self-hosted VLLM deployment can often be as simple as changing the baseral variable in your code.
That's it? Just one line of code?
In many cases, yes. No need for SDK migrations, no custom code rewrites, no building new client wrappers, just to talk to your own highly optimized server.
That abstraction is arguably as valuable as the performance gains.
It really is. It completely addresses that third initial challenge and explains why these specialized inference engines are so rapidly replacing the more generalized deployment tools. It just simplifies the entire pipeline.
So let's look at what this looks like in practice.
Okay. The experience, as we noted, is designed to feel almost identical to using a managed API endpoint, just one you control.
So the first step is just getting it running. You start the server with a simple command line, pointing it to the model you want to deploy, say Llama 3.8b instruct.
And that one command handles all the complexity, loading the model into GPU memory, managing the tensor allocation, and exposing the standard V1 endpoint.
And from there, you just send the request.
Use any standard client, simply directing the base role to your local VLLM server address.
But models get huge. What happens when Llama 3.8b isn't big enough, and I need to scale something like Llama 370b, which needs multiple GPUs just to fit? That used to be a massive orchestration challenge.
A nightmare. You were manually sharding weights.
Right.
Now that complexity is reduced to passing a single integer parameter when starting the server. Tensor parallel size 4.
Just one parameter.
You pass 4, and the system automatically manages the sharding and parallel execution across 4 GPUs. Scaling a model goes from a major engineering project to just passing a parameter.
And tying back to the LoRa flexibility, if I have a base model and, say, 3 personalized, fine-tuned versions, how do I manage serving all of those variants from one simple startup command?
Again, it's simple. You just specify a directory path when you start the server, for instance, LoRa-path.adapters. The system then manages those per-request adapter swaps without duplicating the huge base model memory.
Giving you that massive efficiency for diverse workloads.
Exactly.
This is all great for resource management, but let's connect it back to continuous batching. If I'm the developer, do I have to write custom batching logic to ensure my GPU is utilized 99% of the time?
Not at all.
Yeah.
And this is the beauty of the engine abstraction. It's designed for application builders. You get the automatic continuous batching benefit simply by requesting multiple output sequences in a single call.
For instance, setting the number of outputs n to 32 in my completion request.
Exactly. That single, simple API call automatically triggers the underlying continuous batching benefit without any additional specialized configuration. The system manages the efficiency, you just manage the application logic.
So we started this dive with the unique demand-in nature of LLM deployment. We recognize that latency, memory fragmentation, and unpredictable load are unique killers for traditional ML infrastructure.
And we found that specialized engineering is the indispensable key to overcoming them. The innovations we've discussed, continuous batching for utilization, Pagedattention for memory efficiency, smart scheduling for latency, these are fundamental engineering
They
solutions.
really are.
They translate directly into massive cost savings, higher throughput, and lower latency in real-world AI applications. They abstract away all that complex GPU management into simple API-compatible deployment steps.
For you, the learner, this knowledge means recognizing that the infrastructure hosting the model is just as crucial and often more complex than the model training itself.
That's so true.
A beautifully trained Llama or Mistral model is economically unviable if it takes 10 seconds to respond to a user or if it fragments your expensive GPU memory instantly.
Which then raises an important question for you to consider. If these specialized inference engines allow us to host models that are both significantly larger and capable of handling much longer contexts, think hundreds of thousands of tokens on the same hardware we used last year.
Right.
What new types of deeply contextualized, truly stateful, high-throughput AI applications become economically feasible now that were simply impossible just a few years ago?